Hi everyone, this is going to be a review of selection sort. So what exactly happens in selection sort? Well, all that we do is we keep taking the minimum element out of all the people that haven't been sorted yet, and we move that person to the front. Okay, let's just quickly see it in action. I think it will make sense. So the minimum out of everybody is 1. We'll take 1 and we'll put 1 in the front. Okay, now, let's say these are all of the people that haven't been sorted yet. Okay, so I'll call them the unsorted group of people. So the minimum out of the unsorted group of people is 2. So we'll take 2 and put 2 in the next spot. Okay, and then we'll repeat this process. We'll take 3, which is the minimum out of all of these unsorted people, and we'll put 3 in the next spot, and so on. Okay, and we can see if we keep executing this n times, eventually this yellow array will be fully sorted. Okay, so that's how selection sort works. Let's quickly talk about its runtime. So the best and worst case runtime of selection sort is theta of n squared, right? And as always, whenever we're given a runtime, we should prove to ourselves why this runtime holds. So let's think about each step in selection sort. Okay, so I'm going to break it up into a group of passes. So we'll call this pass 1, pass 2, and so on. Okay, actually, let's make them 0 indexed. Anyways, so when we look at pass 0, let's try to figure out the total amount of work that we're doing in pass 0. And recall that I like to define work as the amount of steps that we're executing, right? Because asymptotics can be thought about the total amount of work a function does. So when we're looking at pass 0, the amount of work that we do is n work because we have to look at all of the elements in the entire array to try to figure out which one is the minimum. Okay, so in pass 0, we do n work because it takes us n time to find the minimum out of everybody in the array. And then what we'll notice is that the next time around, since we know 1 has to be in the front, the unsorted people we have to look at are all of these people right here. Well, how many more people do we have to look at? N minus 1 people, right? And what we can notice is that every time we go down one pass, we're doing one less step of work, right? Because every time we go down a pass, we have successfully figure out where one person goes, right? One more person than the round before, than the pass before. Okay, so let's look at the work and let's try to figure out the total amount of work this function is doing. Well, each time we're just going down by 1, so the total amount of work that we're doing is the sum of this column right here, right? So if we look at the sum of this column, that was not as aesthetic as I anticipated. It's going to be 1 plus 2 plus 3 plus 4 plus n, right? And then we could see that that comes out to n squared if we recall the sum from earlier in asymptotics. So let's move on to the question of why would we ever use selection sort? Well, the first answer is that it's very simple to code. It's very intuitive to understand as well. So the second answer, which isn't as straightforward, is that selection sort actually minimizes swapping operations. So in a very hypothetical example, let's say that swapping is somehow an expensive operation, right? Well, selection sort will do fairly well in this hypothetical example because we only will have a maximum of n swaps, right? Just by how selection sort works. But overall, selection sort isn't the best. It's just merely used as a stepping stone before we get to other sorts that we're talking about, okay? So a quick understanding question, is selection sort stable? And let's recall what stability means. So we say that we have a stable sorting algorithm if for every pair of 2 elements that are equal, they're ordered the same in the final result as in the original list. So let's see what I mean by that. Suppose we have, okay, let's say that we have this following array. Notice that these 2's are equal. So what I'm going to say is that I'm going to call this one 2a and this one 2b to denote that 2a comes before 2b. So if we can ensure that after we sort this array, 2a comes before 2b, then that sorting algorithm is stable. Okay, that's the definition of stability. If we have two equal elements and they're ordered the same in the final result as in the initial result, if we can guarantee that, that means the sorting algorithm is stable. Okay, well, let's think about this in regard to selection sort. Intuitively, it actually kind of makes sense that selection sort is stable, right? Actually, before I talk about whether selection sort is stable or not, I want you all to pause the video and think about it yourself. So yes, pause the video, give this question a go. Okay, so coming back here, I kind of hinted that it seems like selection sort is stable, but it actually isn't the case. And the reason for that is because whenever we take an element, like say we take the minimum, and then we move the minimum in the front, we kind of ruin the ordering that we had before, right? So let's see like a quick example of this. Suppose that we have the array of 2a, 2b, and 1, okay? So when I move 1 to the front, I'm swapping it with 2a. Accordingly, what happens is that our array will look like, right? And now what we can see is that 2a and 2b have like swapped their relative ordering, okay? So when we run selection sort, what will happen is that we will get to 2b, and then we will ask ourselves, is 2a less than 2b? And then we'll say, no, it's not, because they're equal. So then we will keep 2b here, and then we will keep 2a there, right? Now you might say, hey, Soham, like, what if we use a less than or equal to check? What if when I'm at 2b and I see 2a, I say, I'm going to use 2a because it's equal, and I can. Well, in that case, for this example, like, it happens to be the case that it works, but if I take another counter example, like 2a, 2b, and then let's say I run the same variation of selection sort where if 2b is equal to 2a, then 2b becomes the minimum, we'll see that in this case, it wouldn't work because we will swap 2a and 2b, okay? So we can see here that selection sort isn't stable and definitely a very tricky question. So I hope you all enjoyed this video, and yeah, stay tuned for the next one.